Hello, my name is Stephanie Archibald. I'm a security researcher for Cylance, and I want to talk to you about some code I put together for OS X. So basically, a userland kit is like a root kit, except that it operates as a normal user. So you still hook functions to hide. The only real difference is that hooking has to be done on a per process basis. With a root kit, if you hook one syscall, you've kind of hooked it for all processes on your system, yeah? It's still really useful, though, for when exploit chains fail or you need further research to finish compromising a target. It's a lot harder to maintain residency because, of course, once your process gets killed, then you're no longer running. So what are we trying to hide, right? It's the same thing that you're trying to hide with a rootkit. Open file descriptors, processes, uploaded files, heavy resource consumption, like memory or hard disk space, network activity, things like that. And we're trying to hide from the normal sysadmin kind of tools, right? LS, PS, top, activity manager, et cetera, et cetera. Basically, if we get debugged, then we're going to be found because we don't have any real good way to hide from a debugger, right? The code that I wrote kind of comes in 4 stages. Stage 0 is the exploit stage, so it's whatever you're using to compromise your process. That's not going to be covered in this talk because we're kind of after the exploitation stage, right? So the very first stage that we'll talk about is actually our bundle loader. This is kind of a shellcode shim that's used to load a macOS bundle and get it executing in memory. From that stage, our stage 2 is our bundle that basically hooks all of the functions and does our userland scheduling, userland process execution, etc. Stage 3 is whatever you want to be executed that's hidden, right? So it can be shellcode, it could be bash, it could be ls, it could be whatever tools you've written, right? You may ask, why even bother with this stuff? You've kind of gained C execution after stage 1, right? Why not just load up whatever you want in stage 2? But 1 is that it wouldn't be hidden, and then 2, having a framework like this kind of prevents you from reinventing the wheel again, right? Once you have a platform that allows you to easily hide yourself on the system, why not use it, yeah? The thing to note about LAM is that it's 64-bit only, mostly because I'm lazy. And it also had this really cool acronym-y name that I don't remember. So I figured I could open it up as a contest. If any of you guys can create a nice acronym for it that's kind of PG-13, go ahead and just tweet it at ParchedMind, and we'll have a contest. So whoever has the best one after a couple weeks, I'll donate $50 to a charity of your choice in your name. Stage 1 is basically the traditional way to go about executing bundles in memory, from memory on OS X is to find NSCreate object file image from memory and NSLink module. I feel like Apple is trying very hard to forget these functions exist. They've been deprecated since about 2005, but all Apple basically says on their man page is that these routines are programmatic interface for working with Mako files. They bring the Mako files into memory, and the API allows the file to be inspected or loaded into the program. On creation of an object file image, it is checked to ensure that it's valid and it is compatible with the host machine CPU architecture. What they don't say is that the only file type that it'll allow you to load is an MH bundle type, which we'll talk about a little bit later, how to get around that. The interesting thing to note is that they're located in userlib DOLD, which is loaded for every process that gets executed on OS X. So really what we need to do first thing is find DOLD in memory, right? There's a couple of ways to go about it. The really traditional way to do it on other operating systems is to set up an exception handler and walk memory, trying to find allocated memory. Setting up exception handlers on OS X is just really ugly, so I didn't want to do that. I wrote a bunch of shellcode to walk the regions via the VM region recurse64 API, which is horrible and has a bunch of structs that you have to set up and is all just, I don't know, the shellcode was like 65 miles long and it was just really ugly. And then I had a hard drive crash about 3 years ago, and I lost all that code. And then when I needed to recreate it for this project, there was no way in the world I was going to rewrite that shell code. So my husband and I kind of sat down and we started looking at a couple of things that we might use to find it in a different way, right? And interesting to note, if you look at some of the syscall man pages, chmod being one example, is that a couple of the errors that it returns, right? efault, the path points outside the process's allocated address space. Because it's a syscall, it won't chuck a segfault or a bus error if you're accessing unallocated memory, right? So you can loop basically to determine whether an address is allocated. If the address is allocated and you're giving it a pointer, it's going to be to some random point in memory, so probably what you'll get back is enoent, which means that the file does not exist. So here's our pseudocode loop. Basically, you start at some adder. On Sierra, you start at this address here, one with a lot of zeros at the end of it. This is new. In previous versions of OS X, DYLD was always found at the very beginning of the shared region, which is 7FFC something or other else that I always forget. So basically on Sierra, you just have to do this loop twice. The first one is going to be your process's image, and the second one is going to be DYLD. But here you can see we basically call chmod, and then we check for enoent. If we get enoent, we know that that address is allocated, so we can dereference it and check for feedback, which is that image_magic64. It's basically the tag at the beginning of the Mako header struct. The biggest downside of this method is that lots of chmods is going to be easy to detect by any sort of locally running IPS or AV system. But the good thing is that it works for a lot of other syscalls too, right? Basically anything that satisfies that requirement where you need it to return one error code if address is not mapped and another error code for some other error condition, right? Read will work, access will work, etc. There's a bunch of them. From this point, basically what you would do is parse the Mako image to resolve the symbols that we talked about earlier, and then execute them. The constructor will automatically run when NSLink module is executed on an image, so you've gained code execution at that point, right? This is all really common and has been done for years and years, and there's been lots of versions of that talk out, and I didn't want to do it. So I wrote a blog post kind of about it to sort of like, you know, talk about how to get it running on a 64-bit system, because that hasn't been talked about too much. All of the code that exists is quite old and 32-bit related. So if you're interested in that, you can go there and read that code. You'll have to forgive me for that, because they did something to the blog where it used to be all like prettily formatted with courier type and highlighted colors, and it was all very beautiful, and then they went to some other blog system, and now it's all Arial, and it's ridiculously hard and gucky to read. So from that point on, we've got our bundle running, right? So now we're executing in C, which is beneficial, because now we have to kind of hook all of the things, yeah? These are just a small subset of some of the things that we had to hook. I had to hook in order to get this, this code to execute how we wanted. The thing is that hooking is super common. There's lots of research out there. There's lots of talks about it. And it's mostly out of scope. But I kind of did want to detail a little bit as to why I made the choices I did to hook how I did. There's a couple of different choices on OS X as to how to go about hooking. The easiest one to do is to hook the PLT. PLT stands for Procedure Linkage Table. It's basically used for external calls to functions in other modules. And of course, since those modules can be loaded at any address, the linker needs a way to reference those functions. So on load, it will go ahead and update the PLT to have the addresses point correctly. Super easy, you just have to write along, right, to memory. But you kind of run into a situation, and this is how I originally was doing my hooking, but you run into a situation where if your process is loading other modules, loading libraries, loading other things, and those libraries call one of the functions you're trying to hook, that's not going to be caught, right? So then suddenly we're leaving files around and we're very visible. It also, another drawback it had is that it just didn't handle indirect calls. So if for this example, right, I assign my malloc the address of malloc and then I call that wouldn't be hooked, right, because it's not going through the PLT. That's just direct addressing. So the other option is in the function, yeah? It's a bit harder. It requires overriding the first several bytes of the function. You also have to protect the function pages. So depending on what's running on your system, that could be impossible, or it could be highly detectable. But it handles all calls to the function, right? Because you're hooking it in the library, even the ones you don't want. So you've got to think, you're injected into a process, right? A host process. And it's doing random and sundry things. It's probably calling open, it's probably calling, these functions that you've got hooked. For sure, it's probably mapping. You've got to have a way to filter out your calls from those calls. Once you decide to hook in the functions, you can, there's a couple of different ways to go about hooking in the function. So number one is hooking via sig trap. You basically set up a sig handler, which is a lot easier to do now that we're in C. Overwrite the first byte with int3. And basically how that works is it hits int3, it calls your sig handler, and then you have to, if you've decided through your filter that it needed to call the original function, you have to kind of overwrite that byte back, call the function again, and then continue execution. It's really racy, because if you're in a multi-threaded environment, you're in a browser or whatever, then a function gets called while it's not in int3, you're going to have problems, yeah? You're going to miss calls. So then I think the most common way to do it is just with a relative jump. It's nice because it's only 5 to 8 bytes. You can see on the left-hand side here, we have our basic function prolog, push RBP, move RBP, RSP, and then sub RSP to make room for variables. And here you can see you overwrite that with just a jump OX deadbeef or jump whatever address, right? The interesting thing to note is that it's the memory that you write out is basically E9 plus an integer offset, yeah? Which means that you can only reach addresses that are within an integer offset from shared region. When you're executing, usually you're quite far away from that. So that's not really going to work by itself. The other thing to note is that you see these nops that are here, right? If I had written just jump deadbeef and then not nopped, it would have truncated one of the instructions, and then you would have had an illegal instruction, basically error. So we have to nop out to the beginning of the next instruction. Hooking via absolute jump is another option, yeah? You kind of need a method that doesn't use registers. I kept trying to find one register that wasn't very used, and that's just impossible. So basically I found this method online, and you push the low bits and then you move the high bits onto the stack, and then you just ret, and it'll jump to where you want to go. The biggest problem with this method is that it's 14 bytes, which, as you can see from our example, 8 bytes past the start of the function, we have LEA, RDI, and then we're referencing from RIP. Later on, when we decide that we need to call this function for real, and you've copied these bytes off to some fix-up somewhere, and you hit that instruction, RIP is, of course, not going to be the value that the program was expecting. So you're going to try to load from random memory, right? And it causes problems. So basically, you just got to combine absolute jump with relative jumping. So what I did is I just mapped a read-writable page out by the shared region, and then I used that for an array of hooks, basically. And this here is just a representation of my struct in memory, right? So I saved the function pointer that I'm overriding, so that way I could basically walk through these structs to find a hook that I want if I need to in future. There's fix-up, which is basically, if you look back here, you can see it's just the instructions that we overwrote with our relative jump. And then there's an absolute jump there, right? So basically what this is what this is going to do is it's jumping bytes number into the function that we're trying to call, right? Because you got to remember, if fix-up gets hit, we're actually trying to do the original function call, right? It's for cases where our filter has decided that we're not in a process that we care about and we actually need the proper code to run, right? So it's jumping past the bytes of our overwrite. And then we have our trampoline here, which basically does an absolute jump out to whatever our hook function is, right? Yep. So I was kind of a bit vague there, and I just said you jump bytes into the function, right? The number of bytes is going to vary depending on the function. It will be some value between 5 and 8. But yeah, most people will include a disassembler to sort of determine how many bytes to jump on the fly, so that way you know how many to knock out. I was just really lazy, and I put a variable in there. So it's not portable. It's, you should probably use a disassembler library. But again, this is kind of proof of concept, and it was easier. So now that we have a way to hook things, what are we going to hook, right? One of the things that we talked about hiding was open file descriptors. Pretty much, if you have a lot of pseudo processes, or you have a lot of activity going on inside of a host process, you're going to have a lot of open file descriptors maybe, and it could be very noticeable if somebody runs something like LSOF or things on the host process. So what I implemented was what I call open on demand. It basically, you keep files closed until they're used, and then you store the information when open is called, right? So the function declaration for open includes path, oflag, and then an optional mode. So we store that off, and then we also set pause to 0 because it's 0 at the beginning when you open the thing. I do open the file temporarily just so that way I can weed out any file open errors that might have been called and handle those kind of naturally. But then I return a fake file descriptor. Once you're returning fake file descriptors, you're now obligated to sort of hook all of the functions that might use those file descriptors, yeah? So read, write, lseek, close, but also things like socket, or not socket, I just blanked. Some of the network functions as well. And at the very beginning of the hooked code, you basically try to determine whether your file descriptor is fake or real, right? I just did it super easily with a mask. And I basically set the mask to a high value because file descriptors are incremental generally. So you can kind of be relatively sure that you don't hit that high of a file descriptor, hopefully. If the file descriptor is not fake, then you just go ahead and pass it off to the original function. And that's why we needed the fix-up that we had earlier in the slides. So at that point, on a read or write, basically you'd open the file, then seek to the position that we have stored, perform our operation, and then close the file. We have to update our position then, and we also have to kind of handle seeking, yeah? And the way that I handled seeking was just to update the position variable inside my struct, yeah? So for seeks, we don't really have to open and close the file. What we do have to do sometimes is stat the file to determine its size if we have something like seek end. And I'm not handling right now if you try to seek way past the file or whatnot, it'll just put the position there. So that could cause some trouble possibly. It might be something that I want to handle in the future. Because we're in user land, basically, we can only modify the processes that we're injected into, right? We have no real way to hide processes that are created. So my solution for that is just to basically prevent processes from being created by emulating processes with threads. Basically what happens on a fork when a new process is created, it copies off all of the process memory, right? Which means, like, clearly, if you modify the memory in one process, it's not going to affect the memory of a different process unless you've got some shared memory thing going on. But for the most part, that's the case, yeah? Not so for threads, yeah? When you create a new thread in a process, it shares memory, it shares the process memory, which means that you end up in a race condition where if you are jumping to, you know, you have your pseudo fork and you jump back to the same instruction after the end of fork for both the parent thread and the child thread, you end up with this where it might try to modify the same portion of memory, which kind of indicates that we need something like user space scheduling. If we can limit our threads that are executing to one at a time, which is limit our pseudo processes to running one at a time, then what will happen is you have a scheduler thread that basically runs in the background, and every, I think I've got it set to like 1 microsecond, it will suspend the current thread, copy out the thread info, switch current thread, copy in the new thread info, and then resume. On OS X, the type of threads that they use are called mock threads, and the struct related to those is called thread T. They're super low level, they're difficult to set up, but they're also very, very flexible. You can set registers really easily with thread get state and thread set state. You can also use a kernel syscall to suspend and resume them, which is super helpful for what we're trying to do, right? It can cause issues because basically POSIX functions expect POSIX threads, which are p threads, and a lot of them will call this function called pthread get specific. If you've created a mock thread directly with thread create, then it hasn't allocated any of the associated thread storage, right? And you'll get lots of crashes. That function there is kind of my nemesis. We'll talk about that a little bit later. But Mako also provides a pthread interface, which is pretty much a POSIX compliant wrapper for mock threads. The beneficial thing is that you can actually retrieve the thread T from the pthread struct using this function here, pthread mock thread np. But it also provides a pthread create suspended np. This is super useful because otherwise you kind of end up in this race condition, right? I tried for a really long time to kind of use pthread create because I didn't know this function existed. I don't think it's very well documented. I only sort of ran across it when I was reading libpthread, trying to figure out how to go about allocating that, the TLS. But basically what happens is that if you are depending on 2 threads using the same stack and you start one up, it doesn't really matter how many instructions it gets before you manage to halt it. It's modified the stack somewhat, yeah? Potentially. So you've got an issue there. Pthread create suspended means that it's not going to modify the stack at all. So a couple of slides ago, I just said, copy out thread info and copy in thread info. So what I was talking about is just kind of the register state, any heap pages that are associated with the thread, and the stack associated with the thread. Which kind of means that we need a way to determine which chunk allocations are associated with our process and not to the host process, yeah? Because if you kind of think about it, if you're just running malloc on the normal allocator, then you're going to have kind of the host process allocations interleavened with our process allocations. And it's going to be a lot trickier to sort of track what we need to copy. OS has this concept called zones. Pretty much it's how it handles allocations. It uses the default zone. Each zone just has a struct pointing to all of the zone allocations functions. You can see it here. This is from libmalloc, but it basically returns default zone, malloc. You pass in the zone and then the size. You can create your own zone via malloc create zone, which is really useful because then in our hooked functions we can pretty much just hook all of the page allocation functions, so we know those are whole pages, so we can sort of copy those in and out at will. Create a zone, and then any of the pages that get allocated for that zone will automatically be added to our copy in, copy out structs that we have already set up. Track all of the page allocations that happen. And then basically you just sort of hook your malloc, you hook your calloc, VM allocate, all of those functions, right? And then redirect them to using the zone that you've allocated. And because the zone will then, return chunks of memory from our zone, we already know that we're writing those pages in and out as necessary. What didn't work, which is kind of hilarious, I originally tried to do copy on write, where you mark kind of all the pages, read, execute, and then you catch when somebody tries to write to those pages, right? The idea being that this would be a bit faster, so you're not having to write all of the pages, even the ones that are not writable, every time. But we already talked about it with chmod, right? If a syscall is happening, you're not going to get a sig bus, yeah? You're just going to get an error code return. So that wasn't possible. So once you kind of have scheduling and paging, right, you need a userland exec. And this is actually going to be very similar to what we talked about a little bit with stage 1. You load your binary into memory, you call ns-create file image from memory on it. Thankfully, we don't have to find it again. Call ns-link module, and then you can find and jump to the entry point. So find an executable entry point is pretty easy, right? You just sort of walk the Mako struct to find the load commands, and you can see here, what is this? Oh yeah, no. So you may remember that I said earlier that the only type that ns-link module will allow you to load is an mh bundle type. Fortunately, it's really easy to correct. And if you sort of set the type to mh bundle, even if it's not that type, ns-link module will work just fine. So you can actually get away with loading executables with these functions that are supposed to disallow it. ns-link module returns an ns module struct, which means that you then need to find the Mako header offset within the ns module struct, and it's different depending on what version of OS, Mac OS X you're running. Pretty much all I did was I altered the same chmod function that we used at the very beginning in stage 1, but I had it, instead of walking pages, I had it walking ints, and then I also dereferenced because there's just that little extra bit of indirection within the ns module struct. Once we know where the base is, basically, of our Mako image that we're trying to load, we can parse it and find the load commands. I was a little bit lazy here too. I kind of just looked for LC main. There's sort of like a relic system where it uses LC Unix threads, and you have to do this whole other different thing. But this worked for what I was doing, and most modern executables will probably run fine. If you're trying to be exhaustive, though, you should probably handle both. And basically what you do is you take the base that we found and you add the entry offset. This is also new in Sierra. It used to be a different, I think instead of adding to the base, it was something else. Like the entry offset was just the address of the entry point. So now that we can kind of execute what we would like arbitrarily, we might talk about swapping out to disk, because again, we're trying to reduce our resources. Manual swapping to disk is of course easy to implement, right? But it could be detected by AV. One idea that I had was to use mock IPC endpoints, where basically you're moving the storage of our pages off to a different process. And so we're sort of distributing the load a little bit from our userland kit. The only two options that you have to have is that it has to be able to send and receive arbitrary data. Mock IPC endpoints are just kind of a way to communicate with other services on the system. There's a large array of daemons and stuff that are running on OS X that use this, various APIs to communicate. If you can find one that supports out-of-band data, which is the OOB, that'll allow you to write and read entire pages at a time. You just kind of pass it a pointer, and you don't have to go through the mock. It's just a lot faster to do it that way. One of the APIs that you could potentially use for this is CF preferences. You can see it just has CF preferences set app value and CF preferences get app value. So you'd be able to set values. You'd basically just like send it large chunks of data, right, and then retrieve that chunks of data as you're trying to do that swapping in and out. The code for this is going to be up on Cylance Vuln Research /lam. I'll probably get it up there Monday. There was supposed to be a demo here, but I sort of broke my code on the plane, and I need to get home and fix it. So from this kind of really basic platform, kind of what other kind of things could we implement, right? Because now we've sort of got the basic things. Things I really wanted to try to do was implement kind of a shadow cache of loaded files. So the idea being that, over the network, you could send ls or something, and it would sort of load into the shadow cache. And then the next time you wanted to execute ls, instead of grabbing it from the disk, it would just use the image already loaded, right? This would be a really good spot where you could kind of use that mock IPC stuff, because then you could sort of like use other processes to store your files as well. Also, you just hook more things. Like, there's so many things I ended up hooking for this code that it's a little ridiculous, but I didn't really touch any of the network stuff, right? I think it would be really interesting to sort of mask yourself in existing network activity. So if you're injected into a browser and they go to request a website, then that's when you send your data, Other options is to just basically spread around the system, right? I don't know of any real good ways of doing it in memory. I think a lot of the existing techniques have been kind of squashed, but you could, modify the system. It would be really detectable, though. So that could be some interesting research that I'd like to see. The other idea that I had after I kind of got done writing what essentially was a very tiny little OS was, what if you just injected user mode Linux, right? You'd have to kind of write a shim to be able to access the host file system. But I think that could be really interesting, especially if we use some of the other techniques to try to get the memory load down. So other than that, it's just questions. I'm so sorry it was a bit short.
Okay, who was the first brave person?
Yes,
I'm
sir.
gonna flip a coin between the two of you. You just happen to be closer. I apologize.
You mentioned injecting into browser processes. Have you done any testing on this in a sandboxed environment? And I'm just curious how much of it is still applicable in a sandbox. So
I haven't really, to be honest. It was kind of one thing I intended to do and I didn't get around to it. I know that this CF Preferences API is accessible from Sandbox, but I don't really know about anything else. I think once you get kind of code execution, if you're hooking functions, you should be fine, right? I don't really know.
Hi, a lot of those hooking techniques you talked about involved overriding the actual instructions of...
I'm sorry, I can't hear you.
Oh. A lot of the hooking techniques you talked about involved overriding the instructions of those standard library functions. Are those in actually writable memory, though? Because I figured that might not be the case usually. Or at least on Linux, I don't think that's the case for executable code. So is that different on Mac OS?
I'm not sure what you're asking. I'm sorry.
So for those hooking techniques, you involved replacing...
More like a rapper, buddy.
Oh, rapper.
Gotta really...
Okay. You cannot hear me?
Yeah.
Sorry. One more try. Your techniques involved overwriting instructions, right?
Yeah.
But I would expect that those instructions wouldn't be in writable memory due to memory protections and stuff like that.
Yeah, that's why I was saying we have to unprotect them writable, which is where I was saying it would be a bit detectable, right, from an AV standpoint. Yeah, you just have to unprotect the pages. You basically, you mask off and you try to determine what page that instruction is on, right, by anding with not OXFFF. And then, yeah, you just unprotect the page.
Okay, sure. Thanks.
Cool. Who's next? There's one way back there.
Hi, cool talk. One question I had. Would it have been feasible to create a mock process prior to your research and actually take some of the structures that were a little bit more challenging to create and just copy those into the process that you compromised and then run your mini operating system using those primed values? Does that make sense?
I'm not sure what you're asking. I'm sorry.
So basically you create a controlled process and you create, say, like your pthread structure that you need to manipulate. And then what you do is you dump that to a file, and then when you start running your mini operating system, you actually inject that pthread structure and then update the values accordingly so that your mini operating system operates correctly. Would that have been a feasible approach?
So from what I understand with OS X and the thread structures, thread storage system, it's not very well implemented, right? There's a lot of times where it crashes. If you Google around for it, it's very buggy. And so my biggest problem with it is that I'm not entirely sure how it's allocated. The reason I don't have a demo is because of that function. It just randomly, I'm not entirely sure what I changed, which is why I really need to go back home to my main box and see what was different about the code. But it just suddenly started giving me problems with that same pthread get specific function where it was just crashing whenever printf was called. And you know, it's just not very useful to have a userling kit that doesn't allow you to call POSIX functions, you know.
At least.
Other than that, I tried really hard not to touch disk, so I wouldn't. I mean, unless you use some of those APIs to use a different process to do it, I would try hard not to touch disk, so that way you'd be less detectable.
Good. Okay, well, thank you very much. Oh, we have one more question. My bad. Actually, we have two more questions.
So, forgive me if this is a stupid question, since I'm not very familiar with Mac OS X, but like, couldn't you do the same sort of process manipulation with ptrace, and why not use ptrace?
I'm pretty sure they disabled being able to ptrace without root on OS X. So we're in user land, so you won't be able to do that. So.
Okay. That was a simple answer.
I may have missed something, but how do you locate the functions in memory, the ones you want to overwrite?
So if you look back, you remember how I said that one of the problems with, let me try to find the slide real quick. One of the problems with the hooking mechanisms with hooking in PLT was that direct memory offsets or direct memory access, direct function access was not supported. You basically do that. So there's and I thought I'd put it in here, but maybe not. Basically, my hook function will take the function that you're trying to hook as a variable, and it'll use that address because the compiler will go ahead and, at load time, DYLD will go ahead and stick the proper address in there, so you know which address to overwrite.
Okay. I'm going to try to let people ask follow-on questions because it tends to be a dialogue where the first answer is like verbal and then people are shouting across the room. Is there any more questions? Nope. Well, thank you very much.
All right.